Hi, I'm Mary Brady, and this is Lab 5 at Georgia Tech's Physics 2211, and this is the Choose Your Own Adventure, and I'm doing this on the human rocket. So the purpose of this lab is to model Felix's free fall using the physics principles, approximations, in Python, and to find an appropriate model for air resistance. The fundamental principle I used was the momentum principle, net force is equal to mass times acceleration, and the result is Felix ended up breaking the speed of sound, which was his goal, and the air resistance can be modeled as drag force. So you can kind of see here, air resistance is opposing the motion of falling, which is due to gravity for the skydiver. So the main physics ideas, so the velocity update formula and position update formula are derived from the momentum principle. Drag force, here's the equation. It is equal to the coefficient of drag force times speed squared times j hat. This is the equation for gravity on Earth, which is negative mass times gravity, and it acts in the y component. And gravity and drag forces act on the falling object, affecting the object's velocity. So the initial condition, so the system is a skydiver and the surroundings are the air and the earth. The initial position is 36,576 meters above the ground. The initial velocity is 0 meters per second. The mass of the skydiver is unknown, so I used the mass of the average man plus the 70-pound suit to have a mass of 122.47 kilograms. The speed of sound is 343 meters per second, and our skydiver in the experiment ended up reaching a top speed of 377.12 meters per second. And the time elapsed was 228 seconds. So the goal is to try and have my experimental or my computational model get to the top speed that he did. So I plugged in my initial condition, so my mass, my initial position, my initial velocity, the gravitational constant, and also the coefficient of drag force, which I found just through the guess and check method to be 0.009. So here's my iteration loop. I applied the velocity update and position update formulas. I also said that F net force is equal to the gravitational force plus the drag force. And the result is, so you can see here, the force of gravity was moving downwards, the force of drag was moving upwards, and you can kind of see it got a lot bigger towards the end, which matches the velocity versus time graph, which went from linear to kind of horizontal. And we, in the velocity versus time graph, we reach around 360, 370 meters per second. And also in position versus time, it's not linear either. So you can see the drag force acting. So some possible sources of error. I do not know how to find a coefficient for drag force in any other way except the guess and check method. So if I was more accurate in this, I probably could have gotten closer to the experimental result of 377 meters per second. There may have been more forces other than air resistance and gravity acting on the skydiver in real life. Estimating Felix's mass instead of using his actual mass affects the application of the momentum principle. And Felix is not actually shaped like a sphere, like the computational model shows, so some other aerodynamics could have been at play as well. So what if Felix was dropped from a lower height? Would he simply be able to travel faster than sound? So if we use the energy principle and set the change in kinetic energy equal to the gravitational potential energy, we find that the change in height can't be smaller than 6,002.5 meters, since we're using the final velocity equal to the speed of sound. We also are saying that the system is Felix plus the surroundings I said earlier. So we get no work done by the surroundings. So we can set delta U gravity equal to delta K to find this. And what does this mean? So what does it mean that drag force opposes gravitational force? Air resistance is drag force, which opposes the motion of a falling object. This motion is due to the Earth's gravitational pull. Air resistance is from the object pushing through the air particles / molecules and is kind of like a